right, so after that very long example where that convolution took us a really long time and we ended up in the same place as we did in our first example where the reverse of the derivative rule didn't take quite so long, you might be kind of wondering, when do we use these different options? Kind of why did we use this convolution when the other option worked more quickly? So first of all, for the derivative property, that's that one that's L of t to the n f of t is equal to minus 1 to the n dn f over ds to the n. In the forward direction, that's going to be kind of obvious. If you have some t to the n times f of t, then you know that you need this property. The problem is that in the backwards direction, that's going to be less clear. What's going to happen is you need to identify that you actually are dealing with one of those terms. D to the n f over ds to the n. And that's not always going to be really clear. When we did this example, where did it show up? Right here, it was clear to us because we had used that exact same example when we were demonstrating how the forward direction worked. T sine kt led us to this shape function. And then when we saw it show up again, that 2k, right here, that 2 times s over s squared plus 16 squared, we knew to use it. But if s over s squared plus 16 squared had shown up and we hadn't just computed that, it's not really clear that we would have known to use that function there. I told you to remember it, so hopefully you will always see that you can use that function there, but it's difficult to see those rules. So I would say just try to remember common types of terms that show up. And then you might be able to use this property if you get lucky and remember the term at the right time. What's really tricky about this rule is that in the forward direction of this differential equation, we didn't actually use that property. Usually if we use a property in the inverse, it's because we introduced it in the forward. That's how most of our rules have worked up to now. But for this one, even though we didn't use it in the forward, the algebra that we do to solve for capital X introduces this term. And so there's no clue leading us to know that we used the derivative rule, except if we do know it, it makes our jobs easier. The convolution property, L of f star g is equal to capital F times g. Taking L inverse is clear but time consuming. So if you have a product of functions, you can use this property. But convolution to get the final answer, x equal to some stuff or y equal to some stuff, can take a while. And so showing that in the example we just did, there was a product of two functions. It could have been any product of two functions, and we would have been able to use the convolution property. And we can, write down right away that it's a convolution. We can write down the definition, but actually taking that convolution can be a time-consuming process, lots of calculus tricks, especially as the functions become more complicated, the convolution becomes even more complicated. So this method is really flexible. Anytime you see a product, you can use it, but it's also a lot more work than other things. So it's like, I don't know, that saying about using a hammer to fix any problem, like, yes, you could use a hammer for a bunch of things, but sometimes a different tool will be better. And so this is that hammer that you could overuse and probably wear yourself out, but it will usually work. In the forward direction is where the convolution property is actually less clear. And I'll write that on the next slide because I'm running out of room here. So when would we actually use L of F star G? Sort of how would a convolution even appear? In a differential equation. We're using these Laplace transforms to solve differential equations. So if you imagine that you'd have some L of F star G to deal with, it would be because you're looking at something like y double prime minus y prime equals F star G. And then that took you to L of y double prime minus y prime is equal to L of F star G. And every time we've put something on the right-hand side of the equation for a differential equation, it's been sort of like a source term, a driving type term. You imagine that they're things that you would write down a function that depends on time. And so the idea that you would use a convolution can seem kind of unlikely, I guess. And so I just want to tell you that it does come up even though we won't focus on this type of problem. The way convolution appears is in something called an integral differential equation. And so, for example, you could have, I guess we could still use that y double prime minus y prime, and then it'd be equal to like e to the minus rt times f of t, 0 to t. Let's do our tau, I guess. So let's say that was the function. So this type of non-homogeneous part emerges. Oh no, I froze everything. Okay. Just does not like that part of the screen. Okay. Emerges from physical problems. But won't be in the, quote, convolution form. So see, this doesn't look like that nice f of tau, g of t minus tau, or whatever. So the trick here is in manipulating to look like integral 0 to t f of tau, g of t minus tau, d tau. And I won't do that here, but just so that you know, you would have to get this into the correct shape to use the property on it after that.